and hopefully it can also be used to write a certified smart contract. So we develop these certified programming tools, and then use these specification language as a glue to put together these different building blocks and serve it as a modeling and architecture description language. Throughout all these work, we don't just verify safety or partial correctness. We actually verify total correctness properties, and we verify all kinds of security property, resource usage property. So that's the overview of this Certicos DeepSpec project. So what I'm going to do in the next hour is try to sample some projects, some in very, probably very quickly, and some in a little bit more depth to give you and of course this is assuming that you guys have listened to the lecture that done by Ronghui yesterday. So I just want to give a high-level overview of what kind of results we are working on under the DeepSpec project in this expedition project. So on the application side, the DeepSpec team has been working on a DeepSpec web server demo, which you will probably hear more sometime next week. At Yale, we were also building a self-driving car, which run on top of Certicos, and a quadcopter, also on Certicos. So these we try to verify, do some form of verification on these different kind of cyber physical systems. And at Princeton, we were doing verification of user level C programming. You guys are going to hear lots of lecture on how to use VST next week. And at Yale, we were building this compositional concurrent OS and abstract machines. So I will talk more about this concurrent Certicos today. And we are also verifying a real-time Certicos where we actually have a preemption, timer interrupt, and a real-time scheduler. And we try to prove that the operating system is always, satisfies both the schedulability test at any time during the execution, and also provide a temporal and spatial oscillation for those tasks running on this kind of OS. We also have work done over extending Certicos with networking stack and device drivers and so on. So this is necessary to support the web servers. So also, as I mentioned, along the same line, we have been building these, extending the CompCert to support, compilation of a concurrent program. At Princeton, there's a concurrent CompCert project. And at Yale, we are working on CompCert extension so that we can generate a machine code with the flat memory model. Right now, CompCert only generates assembly code with these segment-based memory model, block-based memory model. If you want to generate a machine code, you have to have a consecutive, memory stack. So there's a work on how to do stack-aware CompCert so that you can actually compile things into a C, into assembly code with a single consecutive stacks. And at the machine code level, we are working on integration between Certicos CompCert with, for different backend, but also with MIT's work on RISC-V, which ideally we want to have an end-to-end stack between, from the application level to the OS and to RISC-V to MIT Cami's verification of the RISC-V ISA. So that's kind of the work we are already done, and we have, or at least already started. And so lots of the work that are currently ongoing or we will work on related to, fully verify the DeepSpec web server demo, which is currently work in progress. And we are trying to connect the DeepSpec server and the VST with, this should be DeepSpec web server with the VST and the Certicos. And we are, I will say a little bit about what we do with self-driving car. So as I mentioned, that for the concurrent OS, so we have actually built the first version of concurrent 30 costs, but the semantic model is still under improvement. So I can explain a little bit about how to make our work of supporting concurrency so that it can be generalized to handle distributed systems and so on. And we want to extend the real-time 30 costs to a more general resource-aware 30 costs so that it not only can manage real-time time resource, but also other kind of resource like power or currency or gas. So that's a bunch of tasks that we anticipate to do in the rest of the DeepSpec project. So I guess I just want to reiterate a little bit about what kind of challenges that in the context of DeepSpec project, what kind of challenges that 30 costs project would meet. So one is, of course, if you want to build an end-to-end assurance case for DeepSpec web server or the so-called smart car, you need to really develop these so-called semantic models that can compose these concurrent networked objects. And you need to handle these preemptions. You need to talk about certified linking of these different concurrent layers with verified compilers. And you need to improve the CompCert compilers so that it can generate a machine code. And because the underlying machine model is usually consecutive, but CompCert only generate assembly code, not the actual machine code. So there's a lots of connection work that we need to work on, and that's partly what this DeepSpec project is about. Okay, so I'm going to spend more time talk about this work, certified concurrent abstraction layer. More try to explain what do we mean by modeling these sequential concurrent networked object as a game and played against the environmental context. And then we will talk a little bit about how do we do multi-core and multi-threaded linking, and how do we actually support what we call thread local reasoning. So the net result is we developed these two. We built a certified concurrent OS about 1.5 years or 2 years ago, and we have been improving that proof and build new tools to make that proof cleaner. And so this latest paper published in PLDI 18 is really documentation of the results that we consider as reasonably stable and that can be extended to verify other things. And so I will dive more into this topic a little bit later. Let me just briefly mention that the work on real-time 30 costs is an effort that try to actually extend the machine model with timer interrupts, timing registers, so that at every instruction tick, you would actually increment the timing registers. And you add the notion of a preemption. You can have a hybrid scheduler where real-time tasks are scheduled using a rate monotonic priority-based scheduler, and the batch task can be done using round-robin. And we actually have developed a notion of virtual time or virtual timeline, where it's kind of like a virtual memory. Everybody here understands that OS implement virtual memory using page tables. And the reason why you use page tables is so that every user process has its own view of memory, and their view of memory will not mess up another user process's memory. And that's how do we prove the oscillation among different user processes. That is, one is not going to mess up another, regardless how it behaves. It turns out that in order to prove the temporal oscillation, we would have to introduce something like a page table for time, which maps from virtual time to the physical time. Even though none of today's machine ever implement a page table for virtual time and the physical time, because there's no need. But in order to do that kind of a temporal oscillation proof, we actually logically introduce these auxiliary state to, just to say, pretend it actually built this table, then the proof of oscillation become very straightforward, temporal oscillation, and that's actually what we have done. So So another project is we were working on this thing called the stack-aware CompCert, where CompCert, surprisingly today, don't really have a clear notion what is the stack. All the stack allocated blocks are thrown into the mix of memory, and you don't actually know how these different stack blocks or stack segment, how do they connect to each other, and there's really no guarantee that whether CompCert will run out of generated assembly from CompCert will run out of stack space usage or not. And for OS, we really have to reason about that. So there's actually a project ongoing where we try to modify the CompCert so that not only we control the amount of stack you use, but also we guarantee that all these stack blocks can be merged into a single consecutive stack. And furthermore, even if you have a tail call and so on, these issues are addressed. And then this is actually a prerequisite if you want to generate a machine code, where if your stack is not merged into a single stack, you cannot actually generate the raw machine code. And that's partly why CompCert today only generates the assembly code. So, and then there's also ongoing work on how to connecting, like the VST and the DeepSpec web server with Certicos. The demo of a DeepSpec web server is supposed to run Certicos down below with the web server implemented in VST, verified using VST, and then the quick check and try to do testing of the web server spec and so on. So in order to connect these pieces together, you need to match these different interfaces, and so that's one of the ongoing projects. Let me briefly talk a little bit about the so-called self-driving car projects, just to sample what potential application can be done when you have a certified OS like Certicos. So a few years ago, when we started working on Certicos, Certicos runs on a unmanned ground vehicle called Landshark under the DARPA HACMAS project. And there, our goal was to defend a hacker attack for security. That is, if Certicos can be used to bootstrap different virtual machines, each one of them running different version of Linux, and some are running direct user process, we can prove that even a hacker take over one of the virtual machine, it cannot hijack the whole system. That's the kind of a main motivation. When we work on self-driving car, we realize it turns out that people don't actually, security is never on their radar screen. Like right now, first they want the car drive, right? Before you can call it a certified self-driving car, not a certified stationary furniture, you first have to let this thing drive, right? And security is way, way, way down the pipeline. In fact, even if you had a car running, most of us probably don't care people attacking you because we're not that interesting, right? Well, people could have shot us rather than hack the code and to let you disable your brake and then kill you that way, right? So what's more interesting in the certified self-driving car community is accident. Is what happens if your car gets into an accident? What happens if a self-driving car crashes into a manual driving car, or a luxury self-driving car crashing into a poorly equipped camera-only self-driving car, and you would be arguing who should pay the price. If there's an accident, you kind of have to, one side have to, or two sides have to pay the cost of the damaged car, right? So what we thought is interesting is accountability. That is, the safety of the self-driving car can only be improved if any time there's an accident, we can kind of blame one of the components on one of the car, or at least identify what have gone wrong. So the project of certified self-driving car is mostly try to figure out, is it possible at any time when a car gets into an accident, we have some kind of a black box on the car that from that you can actually uncover what's going on, and then blame, say, oh, this accident, it looks like it's this particular camera module that caused all the problem, or it's this planning module that caused the problem, or this software didn't follow the official rules for driving in New York City, because there's these specific rules. And in order to do that, a certified OS kernel can help because it can help you guarantee the integrity of the log you make. It can guarantee the integrity of the monitor you add surrounding all these components. And so we feel like that kind of thing will be very important. And it's related to the notion of a certified heterogeneous system because in the future we will have all these robots, right, or self-driving car where it contains many of these components manufactured from different companies, and each of them say my components works. But if they say it works, but their components didn't work, and after accident you cannot trace back to the responsibility back to that particular components, then it's not very useful. It's you would not make progress. So this kind of work we do is try to figure out, is it possible to actually establish a certified platform where each component, you have a way to blame each component. That does not mean you have to verify every component, but you have to make sure that a proper monitor or wrappers or safety monitor is attached over all those unverified components. So I guess that's just the high-level overview about some of the ongoing projects, and then I'm going to dive into some of these projects in detail. Are there any questions about the things I have said so far? No questions? No controversy? Everybody? Yeah?
I didn't quite hear, but did you say that you use Certicos in the HACMS project?
Yeah. Okay. It was developed with major funding from HACMS, so it is part of the HACMS. Yeah.
Okay.
Yeah. Any more questions? Okay. So what I'm going to do is to first say a little bit more about concurrency. So this is a work that we just presented at PODI 18. Ronghui presented that talk, and so I'm going to step through an example just to show you what the certified concurrent abstraction layer is and why it's related to stuff I was talking about, the game semantics and the linear logic, and what does that exactly means. To give you some idea what kind of interesting technique you could develop to reason about concurrency. And Ronghui has already shown some of these, but this one is getting a little bit more into detail. So I think just to do a quick overview, we'll try to build a complex system that consists of C code and some assembly code. And occasionally you might even have C code with inline assembly. And these C code, of course, these modules will have some dependency, and you put together to compose this complex system, and you want to verify each of them. But then, of course, you also have to compile each of them into assembly code. And furthermore, these complex system might run different CPU, and the code itself might involve multiple threads. So a complete verification basically means you have to verify the whole system, right? And you might use a lock, fine-grained locking, to protect these two sides. And you have all kinds of concurrencies, I/O concurrency, multi-threading. So one of the things that when we work on OS we find is it's not like we want to solve these problems. We are forced into the setting where we have to start from concurrent setting. That is, concurrency is no longer add-on. We don't do the convenient academic language design. We first design the sequential language. And after 5 years, we say, oh, we also want to support concurrency. Let's add this library called spawn, fork, yield, and so on, and we are done, right? Oh, and if we want to support a distributed system, we add these things. Now, if you are trying to verify concurrent OS, by the way, there's no such OS that's not concurrent. If somebody is telling you they are verified sequential OS, that's a joke, all right? There's no such thing. Every OS have some notion of a concurrency. There's a multi-core concurrency, but there's I/O concurrencies seems to appear almost in all kinds of OS. Of course, OS kernel can disable all the interrupts,